Hello again. Thank you for joining us on another episode of Space Nuts. This is a Q&A edition where we take audience questions, we write them on a piece of paper, and then we throw it in the bin. Or we could answer them. We'll do the latter. We've got questions about ultra-hot Jupiters. We've also got questions about reusing spent rocket fuel. How would you do that? That is the question. And, wow, how about this one? Some conspiracy with the Artemis 2 mission being fake. We'll deal with all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to try and sort all that out is Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Good afternoon. How are you going?
I'm all right. Please forgive me if there's some background noise. There's a gardener working just out the front, and he's doing a fabulous job, but he's using that kind of equipment that you would, demolish a building with.
Yes.
So it's making quite a noise, but I've got my filter turned on, so hopefully it'll just keep it blocked out.
Oh, it's amazing
You just
how
never
well
know.
these things work. I use this microphone in front of me for my teaching. I've had a number of occasions where the dog has decided that I'm paying too much attention to my students and not enough to her. And it's got quite vocal about that, lying just behind me here next to her fire at the minute, keeping her really happy. And they say, no, we can't hear anything. It's amazing how well it can filter out the background noise.
Yeah, the technology is amazing today. It's like the telescope technology that exists now where you can filter out light pollution. I mean, I don't know how that works, but it's quite incredible these days. Works really well. I want to answer some questions.
Of course.
All right, let's start with David, who's on the Sunshine Coast in Queensland, Australia.
G'day, David from the sunny coast again. I just had a question regarding the Ultra Hot Jupiter article from the latest podcast. In the conversation, Fred mentioned that the belief is that stars and their surrounding planets all form from the same disk of material. I just had a question regarding that material. We tend to think of stars as helium or hydrogen or both, and everything else as metals. And we believe those metals formed within stars due to the fusion burning. Where then does this material come from in the disk to form a star and its planets? Is that from material do we believe it's material from another star? Or is there some other process going on? Thanks very much for the show. Awesome. See you guys.
See you, David. Thank you very much. That sounds like it's right up your alley.
It is. It's a good fun one to start off with. So you're right. The material that forms a star and its planets has been contributed to by many previous stars. If you imagine after the Big Bang, the universe was hydrogen and helium and a tiny little bit of other stuff, but it really was barely any, which meant that a generation of stars formed that were pretty much just hydrogen and helium and very little else. Those stars in the early universe, there's some speculation that there may have been including mega stars much bigger than something called the Eddington limit, which is the maximum size that a stable star can form, because of how dense the universe was at the time, how much material there was. So the speculation of stars up to several thousand solar mass. Those stars lived fast, died young, put material back out into the cosmos. So when they died, they locked some of the stuff up in the remnants that are left, whether that's a black hole, a neutron star, a white dwarf, whatever. But the material that was flung outwards to form planetary nebulae, supernova remnants, disperses into the wider galaxy. So what's happening over the eons of time since the Milky Way formed is that stars are born, live, and die. And when they die, they pollute the cosmos. Stars have different masses throughout different things, but what that means is that you gradually get more and more heavy elements introduced into the galaxy. And that goes to basically contributing to the composition of the gas and dust that floats around in our galaxy. If you go out, particularly this time of year in the southern hemisphere, But if you go out on any night of the year where you can see the Milky Way, you'll see that in the band of the Milky Way, there are dark patches as well as glowing bits. The dark patches are not places where there is a lack of stars, but rather they're places where you've got huge clouds of gas and dust that are opaque, that are blocking the light from stars that are more distant from reaching us. So they look dark in the same way that a cloud blocking the sun will look dark in the daytime. It's blocking the light from beyond. These clouds can be vast, and they're made of gas and dust and ice. Mainly hydrogen and helium, but lots of other stuff. And that other stuff will vary from one cloud to the next to some degree based on what it has been polluted with. You'll have some degree of stirring of pollution of the galaxy that gives you a background increase in the amount of metals. But you'll also get local variation. We see all of this, incidentally, in the Earth and the solar system. There are suggestions that the solar system, when it was young, when it was forming, was polluted by a nearby supernova that injected a lot of very short-lived radioactive aluminium isotopes that accelerated the degree of melting you got in the rocky objects. There's a signature there of a radioisotope that is so short-lived there shouldn't really have been any of it around unless a supernova exploded nearby to pollute our disk, giving us a slightly unusual composition. There is also an argument that the Earth is richer in gold than it should be because sometime between 10 and 100 million years before the formation of the Earth, 10,000 light years from where we formed, two neutron stars collided, polluting the universe with gold. And some of that gold made its way into the disk that formed the solar system, got incorporated into the Earth, and that's why we are a particularly good place for Goldfinger to have his little layer. We've got more gold than normal.
Yeah.
What this all means is that those giant clouds of gas and dust in space can be truly vast. When they get nudged and start to collapse, they'll fragment in their interiors to form a cluster of stars, a number of stars which form from the little denser bits. It's like driving through a fog bank. Fog banks are never one uniform density. There's denser patches and less dense patches. A denser patch in one of these clouds will collapse under its own gravity, and so you'll get lots of stars forming. As that material collapses in, it collapses down to form a disk around that young protostar that's forming. And the star and the disk are made of the same material. They're forming from the same material. All that material that was in the cloud from which they're formed, which has been polluted over many generations of stars, cooking the books to give the composition that is uniform across that star system. What happens then is that the star forms from everything. So it ends up very rich in hydrogen and helium, because even after all that pollution and all that evolution, hydrogen and helium still make up something like between 98 and 99% of all atoms in the universe. So the star is going to be primarily hydrogen and helium with a thin veneer of everything else. In other words, the abundance of material in the star is going to be very nearly identical to the disk. Star will end up being very, very, very slightly enriched in the heavier elements because from the disk, particularly when the disk is cleared, there will be some infall of rocky and icy objects like the Kreutz sun-grazing comets we see that fall into the star and pollute it further, but that's a very, very small effect compared to the overall mass of the star. The planets that form in the disk, in the main, form through a process we call core accretion. There are some suggestions that some of the most massive stars can form through a process of instability, and those planets and binary stars would form with a more stellar composition, i.e. lots of hydrogen and helium. But most planets will form by initially growing a core of solid material, because when you have a low mass, you can't capture gas. And so, therefore, your composition will be dominated by the solid material, not the gases. So that's why the Earth doesn't have free hydrogen and helium. We simply don't have enough mass to capture those gases and hold on to them. So even though 99% of all atoms in the protoplanetary disk were hydrogen and helium, we didn't get any of them, other than the odd tiny little atom that was captured in a cage of other compounds called a clathrate that was captured in a mineral, effectively. So we barely got any of those materials because we couldn't hold on to them. We formed out of the solid stuff. The further you are from the star, the colder it is, so the more different things can be solid rather than gas, which is where we get the idea of the ice line. If you're far enough from the star, water can be solid, can be ice, and then suddenly you've got a lot more solid material because water is about the most common compound there is almost. It's the most common atom hydrogen and the third most common atom oxygen, and you put them together and you've got water. So beyond the ice line, you've got a lot more solid and you can form planets much quicker, which is why we think Jupiter and Saturn got so big so quickly. They had a lot to feed on. And eventually they got massive enough that their gravity was strong enough to hold on to the hydrogen and helium around them and devour it. So they are in composition much more similar to the Sun than the Earth is, because they have all that hydrogen and helium, but they are still richer in solid material than the Sun, because at their core there was all the solid material needed to build up before they could gather the hydrogen and helium. So they started with more solids effectively. The Earth doesn't really have the hydrogen and helium. So all of the objects in our solar system will have the same composition as the Sun in terms of the balance between carbon and nitrogen and iron and all these elements, except for where they weren't able to capture those elements because they weren't massive enough. So the Earth doesn't have the same composition as the Sun in terms of hydrogen and helium, but it does in terms of iron, nickel, all those things. The balance between iron and nickel and carbon and all the rest of it are all in the same ratios as the Sun, to an incredibly high precision. And that's because we all formed from the same material that, quite rightly was mentioned in the question, was delivered by past generations of stars that had lived and died. And that's where the whole concept that we are stardust comes from. It's the idea that all the atoms that we need to make us, other than the hydrogen atoms, were cooked in the furnaces of stars long dead. All the carbon, the nitrogen, the oxygen, the phosphorus, all those wonderful things, calcium that contributes to our bones, are all stardust from stars that died long before the solar system formed.
There you are, David. A very good answer that pretty well nails it. I like the bit about there being more gold on Earth than there probably would be in other places. So that was a lucky break for us.
Absolutely. And it's so useful for a lot of the technology we use, not just for those who like pretty sparkly-bangly things, but, there's a lot of those rarer type things that are so vital to our technological growth that are all linked to our ancient heritage.
Yeah. There's gold, there's lithium, there's just so many of them. We've got a lithium mine just down the road from us, actually.
And that lithium is probably all primordial. The lithium in the universe is almost all leftovers from the Big Bang.
Wow. That's interesting. There you go, David. Thanks for the question. Lovely to hear from you. Hope all is well on the Sunshine Coast. This is Space Nuts with Andrew Dunkley and Jonti Horner, a Q&A edition. Let's take a short break from the show to tell you about our sponsor NordVPN and to discuss your online privacy. Because let's face it, these days, whether you're browsing at home or jumping onto public Wi-Fi at a cafe or an airport or wherever, your data is constantly at risk. Hackers, trackers, even companies you've never heard of, they're all trying to get a piece of your digital life. And that's where NordVPN comes in. Our sponsor is fantastic. It's one I've been using for many years now myself, and I have absolute faith in their product. NordVPN encrypts your internet connection, hides your IP address, and keeps your personal information safe from prying eyes. It's like putting an entire online world inside a secure tunnel. They've got over 7,700 servers worldwide. You can browse fast, safely, and without restrictions. Plus, features like threat protection and ultra-fast speeds with Nord links mean you're not sacrificing performance for security. You get both. Right now, you can grab our special Space Nuts deal and get 4 months extra for free. Plus, there's a 30-day money-back guarantee, so it's completely risk-free to try. Just head along to our special URL, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts, and don't forget to use the code SpaceNuts. That's nordvpn.com/spacenuts. Stay safe, stay private with NordVPN, our sponsor.
Roger, you're loud and clear here also.
Space Nuts.
And we're with Professor Jonti Horner today with Fred away. Let's go to our next question. Jonti, this one comes from Mark.
Hi, it's Mark from sunny Sidlesham in the UK. I've eventually plucked up the courage to send in an audio question, so here goes. You quite often mention water ice and the possibility of turning this into rocket fuel. So my what do you think sort of question is, when you use hydrogen and oxygen as a rocket fuel, it must turn back into water ice in space. So do you think it would be possible to collect it and reuse it through the rocket engine again, massively reducing the amount of fuel you would need to carry for an extended journey, say, to Mars? I've sort of drawn up an idea, but what do you think? Once again, keep up the great work. Mark from the UK.
Thank you, Mark. It's an interesting idea. My first thought when I first heard the question was, how would you collect it? That might be the first challenge.
That would be a bit of the challenge. I mean, the thing is, your exhaust is being pushed out of the back of the rocket at very high speed in a very dispersed form. Now, the rocket's going forward because you're throwing the things out the back. You've got the momentum being transferred. And it's equivalent, I guess, to you. The way I'd visualize this is imagining, again, sitting on an ice rink on a wheelie chair. So you've got no friction whatsoever, really slippy. And you're holding, normally I'd just say one medicine ball, but instead imagine that you're holding a big bag of shot puts. You throw a shot put away from you and you'll recoil in the other direction. You throw another shot put and you'll speed up and you'll move in the opposite direction to the direction your shot puts are going. So that's how you'll work. And that's essentially what you're doing with the rocket. You're pushing material out of the back and you're moving the opposite way because overall the momentum is conserved between the stuff going one way and you going the other. The problem with the rocket itself capturing its own exhaust, pumping it back in and reusing it, is then you're taking that momentum and bringing it back to you, which means you're getting pulled back towards it and you'll end up having gone nowhere to some degree. So imagine now that situation with the shot puts on the ice rink, but instead you've got a really efficient bungee cord so that when you throw them away, they bounce back and you catch them again. What will happen is as they're moving away from you, you'll wheel away from them. And then as they get pulled back towards you, you get pulled back towards them and you end up where you started from. Module will know a little bit of change due to friction and loss of energy and stuff like that. So the problem I'd have with this suggestion is not actually the idea of capturing and reusing the fuel. I think that will be hard because the fuel will get so dispersed, the water will be scattered out there, and it's just easier to go get a big lump of ice from somewhere than to try and pick up individual water molecules or small grains of ice dispersed over a large area. But the idea of being able to capture it from the same rocket and reuse it would get you into this problem of having to pull back material that you've pushed away, which means you'd be pulling yourself back to where you started from. So you can't get away, I think, from that momentum issue there. So I think it's two different things. I think if you had the ability to, instead of using hydrogen and oxygen as a fuel and burning them to be water, you could instead have a rocket powered by firing pellets of water out of the back. You could fire them at a target that captures them, collect them, and reuse those pellets for something else. But that target will get pushed around by the arriving water pellets. So you'd want to be clever with that, and you'd need to continually change its orbit and stuff. So in theory, potentially you could gather the fuel for use on another rocket without it being the rocket you're flying that gathers that fuel. But in reality, you're dispersing it over such a large area that unfortunately it wouldn't be that practical anyway, especially when we've got just huge lumps of ice floating around anyway. I mean, you and I have both been photographing a beautiful lump of ice flying through the solar system. There we go in the background. That's enough fuel for missions forevermore if we were to go and mine there. And that's a lot more efficient to mine one big comet or asteroid for water ice or mine the moon for water ice than try and catch it when it's dispersed, I think. So it's a really good idea. It's really good thinking, but it's something that wouldn't work. I think that's the way I'd view it.
It'd be very complicated. And as you said, trying to capture it in the ship you're actually propelling would be counterproductive.
Yeah.
Using another spaceship to capture the ice after it's been expelled would be difficult because it would spread out too far. But then you're using the same technology to chase the ice that's been spent already and spending more to get the ice back. So, it's a catch-22. It's just going to keep going around and around. So, it makes it a little bit difficult, Mark. But thanks for your question. That was a fun one, actually. But I like the way people think. But I suppose just to expand on it a bit, there's going to come a time where using those kinds of fuels probably won't be necessary. They're developing all sorts of different kinds of engine technology, everything from solar sails to scramjets and they don't use that kind of fuel.
There's all sorts of things you could do. I mean, again, going back to the Bobbyverse, which I mentioned before, the Van Neumann probes going through, they used kind of ram scoots essentially initially in the books. They then move on to other kind of speculative sci-fi things. But initially the idea of having a fusion drive where you scoop up hydrogen atoms and turn them into helium and push them out the back, where in front of you you deploy a big thing that gathers the hydrogen you're moving through. This is also what they did in Tal Zero by Poul Anderson, is, you're moving really quickly, you gather hydrogen from in front of you and compress it like a ramjet effectively. There's all these kind of things, but they will all, unless we get to truly sci-fi type things like warp drive or orbital air drives or whatever, which require physics to be somewhat different than how we currently understand it, you still have either a source of propellant, which you then get rid of out the back one way or the other, or with solar sails, you're using the stellar wind and that pushes you away. People who are sailors can probably tell you a lot more about the complexity of how you can tack into the wind and move across the wind. But the solar wind is incredibly tenuous compared to the wind in the Earth's atmosphere. So you need a very, very big sail. And I think that would be somewhat limiting if you were wanting to do, I guess, Star Wars style dogfight maneuvers. You wouldn't do that with a solar sail. So people will pick the right technology for the kind of mission that they want. And that was where the Dawn mission, which went to Ceres and Juno in the asteroid belt, was really interesting because it used an ion drive where it was using, I think, ionized xenon. And that kind of drive achieves a much, much lower thrust, but can operate for a much, much longer time. So it's very energy efficient. But it wouldn't be any good for getting off the surface of the Earth. But it's very, very good for cruising around the solar system when you're not in a rush. And so what will happen is I think different people will have different types of drives for different types of scenario and choose the one that works best.
Yeah, but to get off the planet at the moment, you need rockets. There's no real other technology that will get you out there. I know they've been trying sort of catapult technology, which could deploy satellites in the future.
Yeah.
I think you'd need to be in the right place on the planet to take advantage of the rotation of the Earth, so that you don't have, like, you couldn't do it too far away from the equator, that kind of thing. But at the moment, the standard old rocket engine is the best option at the moment. So
part of where the refueling station idea around the moon comes from, which is, if you have to take your fuel with you, you're carrying a lot of extra weight, so you've got to burn extra fuel to carry that fuel, which means you're carrying extra weight, so you've got to take even more fuel to burn to carry the weight of the fuel you're carrying to carry the extra fuel. And so it becomes very inefficient very quickly. So if instead you can have small launches from Earth and then refuel once you're beyond the Earth, that's a lot more effective. And the other thing that people have suggested long-term as a solution to get things off the Earth more cheaply are things like space elevators, which are probably still far science fiction. I don't think we have the material science to do that, nor the political will. I mean, putting that in perspective, just saw the announcement this week that the vast inland rail project that was happening in Australia is no longer happening because it got too expensive and it's taken too long. And if we can't build a railway between Melbourne and Brisbane, it's going to be really hard to build an elevator between low Earth orbit, between the Earth's surface, geostationary orbit, and the same distance beyond for the counterweight.
Yeah.
So I don't see it happening anytime soon.
We can't even get a tunnel under the Blue Mountains between the West and Sydney.
No.
And that's despite the fact that road is currently closed due to a structural failure in Victoria Pass, the old convict bridge that's 200 years old or something, or 150 years old, and it's finally given up the ghost. And so they've closed the road. It's, people have been screaming for a tunnel for decades, and no politician's willing to spend the money because there aren't enough people. Bottom line is there aren't enough people living west of the mountains to make it worth your vote. That's really what it comes down. That's what it comes down to.
Reminds me of the old episode of The Simpsons when I was a kid, with the kind of argument about books for the kids or something. There's just the two people at the front room basically shouting, "But our children, but taxes, but our children, but taxes." And it's this whole thing of everybody wants it, but nobody wants to pay for it.
Exactly. Yes. A tunnel under the Blue Mountains would be wonderful, though. Although some of the arguments against it are, well, it'll only save you 15 minutes. I think it'd probably save you more. It gets pretty log jammed up over that mountain.
We have those arguments about the Toowoomba bypass, and that's been a godsend. I mean,
I used it last year. Yeah, it's fantastic.
It fell apart and bits fell onto it because they contracted fairly cheaply. But that has saved about half an hour from my trip down to Brisbane when I go to the airport and stuff, because I don't have to go through Toowoomba. And all the freight companies use it, even though the tolls are quite high, because the tolls being high is a lot better than the wear and tear on their vehicles coming up the old road into Toowoomba and having to stop at all the traffic lights and stuff. So it works out cheaper for them. It's better for the Toowoomba Council because they're having to repair less potholes and they have less accidents. And it's one of those things where it was a little controversial when it was being built, but since it's there, it's been a godsend. And I'd like to think that some of these big infrastructure projects would be the same. And I mean, a space elevator would be wonderful, but, you know, it's going to be hard to persuade people to commit to building it, even when we get the technology, I think.
Wait till there are orbiting hotels. That'll change everything. You wait and see. Might be waiting a while. Thanks, Mark. Lovely to hear from you. This is Space Nuts with Andrew Dunkley and Professor Jonti Horner.
0G, and I feel fine.
Space Nuts.
One more question, Jonti, and this one comes from Paul.
G'day, Fred and Andrew. Paul here from sunny Bris Vegas. I have a question and a dirty secret that I need to confess. So, I was on this Flat Earth group on Facebook. Yes, I know. Anyway, this guy provided some AI information which was absolutely correct to contend that there is no way that the Artemis mission could have ever caught up to the Earth because the Earth travels a hell of a lot faster than that little spaceship. I pointed out that they didn't need to catch up to the Earth at all. They just needed to point themselves to where it was going to be and then splash down, land safely, and be applauded by everybody except for the flat earthers like him, who are absolutely incensed at the moment about how it's all fake, as per usual. Anyway, I told him that if he really wanted a better answer, exact answer, he really needed to talk to an astrophysicist. So my second question is, well, my first question is, was I on the right track? And my second question is, are there any astrophysicists or any websites out there that can give us an animation of the Earth going around the sun that also has the animated version of the Artemis going around the moon so that we can see the whole thing in context in terms of the solar system, or at least our area of the solar system? It's not going to convince him, I'm sure, but I think it'd be pretty cool to see something like that. Anyway, thanks very much, gentlemen, for the show as always. Look forward to it every week, and catch yous later. Have a good one.
You too, Paul. Thank you. If only we had an astrophysicist somewhere nearby. Jonti, any? I know he was directing the question to Fred, but he asked for an astrophysicist.
Yeah, we are legion for we are many. There's plenty of us around. It was always the thing when I was at uni of what title you use for what you're studying would depend on how bothered you were about the conversation. Because if I told someone I was studying physics, said very quickly exit stage left. If I told them I was doing astronomy, they'd stay and chat. And if I told them I was doing astrophysics, they'd just look a little bit scared. But I was doing all three. This is an interesting one. I mean, people like the flat earthers are difficult because there is no amount of truth, no amount of evidence that you can put before people who are convinced that they've been lied to.
That's it.
Other than talking to them gently about it. And it's like discussions of climate change I've had in the past with people who argue climate change isn't real. Arguing and fighting with people over this doesn't win hearts and minds, it just gets them more entrenched. But talking to them about it and talking about why we think something is the case, this is our evidence, this is what it is, that can be a little bit more fruitful, I guess. But it is really challenging. I mean, especially given that we had a beautiful eclipse of the moon just a few months ago, where you can see that the shadow of the Earth is round. I
Yeah.
mean,
That's the big argument. If the Earth was flat, the shadow at some stage would be just a line across the moon.
I would see the elephants and the turtle. But the other thing is, if the Earth was flat, the cats would have pushed everything off the edge by now.
Yes.
That's the other one. But in terms of Artemis, at the end of the day, we know it happened because we saw it. I was over in Europe at the time, and my colleagues at UniSQ were happily sharing their own little footage of the spacecraft that they got from our telescopes. They have no reason to lie. They have no vested interest in this. It's not like they're secretly on the payroll of NASA. Ignoring the fact that if it was faked, Russia and China would be racing to tell everybody, because that would be the best PR victory ever. And it's the same with the moon landings in 1969. Did anybody really think that the Russians would have stayed quiet if there was a sniff of it being faked?
In fact, my great-grandmother always thought the Apollo landings were faked. She absolutely refused to believe it.
Yeah.
But she grew up in an era before flight.
Yeah.
So I can understand why she would think that, but she just thought it was all just some sort of publicity stunt. But I don't remember what they might have been trying to get publicity for.
Because they beat the Russians. I mean, that's what it was to them. Or beat the Soviets, as it was then. Have been pulled up on that a couple of times.
It was definitely a big PR exercise in that regard.
I had a fun PhD student who worked with me, Dr. Jake Clark now, gave a wonderful talk a couple of times about the moon landings in 1969 and why they couldn't have been faked because we couldn't afford it. Talking about faking it with the technology we had at the time would have actually been more expensive than going there. Which is fairly compelling for me. I mean, there's always a joke that, the moon landings were always going to be faked, but they hired Stanley Kubrick to direct, and he was such a perfectionist that they demanded that they do it on site. Which was always the old joke. With Artemis 2, there is abundant evidence that it really happened. You could, with a small telescope or binoculars, go outside and see the spacecraft. And I mean, you can't fake that. It's not like we're beaming thoughts into your head, and if you think we are, you can wear some tinfoil. That's all good. In terms of the argument that the Earth is going too quick for this thing to catch up, that is, in the kindest interpretation of it, that is allowing common sense based on your understanding of how day-to-day life works interfere with looking at how things would move through space. I can see why you would get to that. If you think about a small child running along with a model of Artemis in their hand and a Ferrari driving down the motorway, or insert other make of car driving down the motorway at 100 kilometers an hour, the child is not going to catch the thing because they're not quick enough. And there are limits on how fast a child can run and how fast a car can move to do with air resistance. It's, however, almost similar to saying, I can't throw a ball up in the air and catch it because I'm moving at over 1,000 kilometers an hour around the Earth, so I'm moving too fast to catch up with that ball. Doesn't work like that because me and the ball are both moving at 1,000 kilometers per hour, and so it's the relative speed between us that matters. The Earth is going around the sun at about 30 kilometers a second. That's demonstrably true. Artemis, moving in orbit around the Earth, is moving around the sun at 30 kilometers a second with the Earth. It's falling with the Earth, so it's a relative speed that matters.
Yep.
Now, if I went above the Earth onto the space station, but instead of orbiting the Earth and falling with things, I was able to use rockets to stand still, or I had an imaginary hovering platform of doom that wasn't moving, I'm out of the atmosphere. If I threw a ball up in the air, it would move away from the Earth, and the Earth's gravity would slow it down and pull it back, and it'd fall back down to me, just the same as how it does on the ground. Now, if I was in orbit around the Earth and I was stood on the International Space Station and I tossed the ball upward, it would actually start moving on a different orbit around the Earth. So while it would move up away from me and it would move down, it'd be going around the Earth on an orbit that takes slightly longer to go around the Earth than I do, so it'd also fall behind. And that would look like wind resistance, but it's actually just a quirk of orbital mechanics in that I've put it onto a different orbit. Because we are both falling at the time I let go of it. So if we imagine our flat earther jumped off a cliff, and I'm not encouraging them to, please do not do this, but imagine one jumps off a cliff while holding one of the shot puts from the previous answer without it being on a bungee cord. And they let go of the shot put will fall with them at the same speed. It won't move away from them and come back. it will accelerate downwards in exactly the same way that they do, and they'll only diverge once air resistance takes effect, depending on which of them feels more air resistance.
It's the Galileo experiment, isn't it?
So if you're on the space station and you throw a tennis ball up in the air, you're both actually falling, but you've changed the speed the tennis ball's falling, so it'll move away from you and not appear to come back because you're both still falling. The reason all this is relevant to Artemis is Artemis boosted off towards the moon at a speed that was not greater than the escape velocity from the Earth. It was a speed that was high enough to get to the moon, and the moon steered it around and flung it back towards the Earth, but then it fell towards the Earth under Earth's gravity, moving with insufficient sideward speed that as it fell towards the Earth, it would miss us. It instead was going to hit us, and they controlled it with rockets and stuff so that it entered in a controlled rather than uncontrolled fashion. Yep. What matters is not the speed the Earth's moving around the sun, or the speed the sun's moving around our galaxy, or the speed that the galaxy is moving through space. All that matters is the difference in speed between the Earth and the object, because they're moving together. This thing's speed was at no time greater than the escape velocity of the Earth, so it could never fall away from the Earth and never come back. It was always going to go up and then come down again, unless they used rockets to boost it into an orbit around the moon to shed some of that energy, which they didn't. They instead slingshotted around the moon to come back. All of that is perfectly rational and straightforward given our understanding of physics, but it doesn't necessarily fit your common sense, because you think about throwing a ball out of the window of your car while your car's doing 100 kilometers an hour and the ball will fall behind you and never catch you up. And so a lot of the arguments that flat Earth believers or other people in that kind of situation are making good faith are built on a faulty groundwork where the common sense of how they understand the world to work is not applicable to the situation they're applying it in. And that's true of things like, the oceans are flat. If you put a spirit level on them, they're flat. Well, it's actually that they're curved, but they're curved at such a small level that locally they look flat. Yeah. It's a subtle difference, but it's one that's easy to miss because it's hard to get your head around those distances. In terms of the animations, I just did a quick Google search for Artemis animation of orbit. And there's some beautiful, the first hit is a NASA flight with an annotated and animated path. There's a few YouTube videos. There is a Reddit link with an interactive 3D animation. There's a lot of little YouTube short videos that pop up which are not to scale. Because if you make things to scale, the sun and the earth and the moon are points that are 1 pixel across, and the spaceship is a point that is a pixel across as well, because nothing can be smaller than a pixel. There is a fabulous thing, incidentally, and I'm going to see if I can find it, see if it's still there. There's this great thing called If the Moon Were Only 1 Pixel. It is... I'm going to see if the website still works, because this is one of the great things on the internet. Here we go. I'm going to drop it into the chat window. This was an effort somebody made many, many long years ago. I'll put this into the public chat, which never gets used. There we go. To visualize the scale of the solar system, if you made the moon 1 pixel across, so the Earth will then be 2 or 3 pixels across, you can, when you get bored of scrolling, you can click play. But if you open that up and then you scroll to the right to explore, you move along, and then you've got the scale. 1 pixel is 3,500 kilometers, so the sun is a fairly big blob. And you scroll to the right from the sun, and you've got a distance at the bottom. Scroll to the right a long way, we've gone 10 million kilometers. This is this fabulous visualization to let you see how big things are.
Oh, isn't that clever?
How fast light travels, you can click, and that's slow. It's fabulous. Now, what you can do is you can skip through. I need to find where there was a way to skip to the Earth. Yes, at the top. Skip to the Earth, goes whiz really quick, goes past Venus, comes to the Earth and the Moon. If the Moon is 1 pixel, the Earth is only 2 or 3, and you get the scale of them 8.3 light minutes out from the Sun. And think how far you've got to scroll to get there. Yeah. Think with that Moon being a single pixel, how far it is from the Earth. This is why none of those animations have things to scale. Because you wouldn't see the spacecraft. You wouldn't see the Earth and the Moon. They wouldn't look pretty. So the caution there is that the animations that you see, even the beautiful NASA ones that show the flight path, are not to scale, and that can be misleading. That can also add to some of the arguments that this is fake, because people say, well, the Earth and the Moon are much smaller than that, and they're much further apart. That looks wrong. So it's worth being explicit that these visualizations are definitively not to scale. The one, incidentally, that was linked on the Reddit page looks like the dots for Earth and Moon actually are more to scale, so I'll just drop that one in as well. Not sure how this works. I've not really played with it, but you can drag the orbits around, you can move them back and forward in time, you can see the in and out of plane stuff, and you can move the visualization around even with the background stars, which is quite nice. So that's worth a play as well, and that looks a bit more to scale. And there's lots of things you can play with. But fundamentally, we could see it. The hardest part for me about the small number of people who have argued that the Artemis mission didn't happen is that it's something that anybody on the planet could see so long as they owned binoculars or a telescope.
Yeah.
You could just point it somewhere and you could see the capsule moving there. If you really wanted, at any time when the moon was above the horizon, you could track it round.
Mm. And if you've got good enough gear, you can actually look at the moon and see the landing positions of some of the Apollos. If you've got the gear.
If you've got the gear, I mean, that's kind of spy satellite level. But what you can do if you've got slightly less of the gear is bounce laser pulses off the retroreflectors that the astronauts left at those sites and measure the distance to the moon and measure its recession to an incredible precision. And we can only do that because people went to the moon.
Yeah, absolutely. I remember the day that Neil Armstrong stepped on the moon. I was sent home from school. It's just one of the strongest memories of my childhood. I was 7 years old, and I'll never forget it. It was quite an extraordinary thing in human history.
Hugely inspirational. I mean, I'm not old enough to have ever seen anybody walk on the moon. I'm hoping that'll change. But the generation of astronomers who are 15, 20 years older than me, who were old enough to see the moon landings and take them in, so many people were inspired to become scientists and engineers by that. We got a whole generation of people across the sciences, across the engineering subjects that changed the world, who were all inspired by seeing people walk on the moon. And it's kind of exciting to me, even ignoring the science, even ignoring the technology, that we're going to get that experience again in the coming years if we go back there. There'll be a whole new generation who will change the world, all inspired by those people touching down and seeing it happen.
Yes. I was very lucky to meet one of them, Buzz Aldrin. Some years ago came here because they built a Wright Flyer at a place called Narromine, just up the road from here, 40 kilometres away, and they took it out for a fly. And he came for the occasion and gave a wonderful speech, and a handful of us in the media got to interview him afterwards in a hangar at the same time as a helicopter decided to take off.
Yeah, that sounds about right. He famously
But you know what? You just go with it.
Oh, he very famously gave very short shrift to people who told him that he'd not been to the moon.
Oh, I know. I did actually raise that question, but gee, it was such an interesting answer. Oh, yeah, fabulous. Paul, great question. Really enjoyed that one. And I can understand your frustration, but maybe just avoid those Facebook pages because you just can't save them, my friend. But good to hear from you. If you've got questions for us, please send them in. You can do that via our website, spacenutspodcast.com or spacenutz.io. You can also visit us on social media. We've got the official Space Nuts Facebook page and the official, Instagram page. We've also got the user group on Facebook, the podcast group, which is it's a lot of fun. It's where people who listen get together, swap photos of stuff they've taken in space and ask questions, and it is a really good group. So the Space Nuts podcast group on Facebook, very much worth joining that one as well. And hope you'll join us again real soon. And thank you to Jonti Horner for filling in for Fred for the last month or so. It's been fantastic, and hopefully we can get that photography special off the ground and get you back and have a chat about astrophotography, Jonti. That would be a real good one.
Fingers crossed. That would be awesome.
Yeah. All right. Catch you soon. Thank you so much.
Catch you later. Take care. Thank you very much.
Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland, filling in for Fred. Fred should be back next week or later this week. I can't get my head around when it'll be. It's a time slip thing. But thanks to Jonti for filling in, and thanks to Hugh in the studio who couldn't be with us today because he's fake. Boom, boom. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.